Before we get into the specifics of our evaporite course, I want to look at the physics of the evaporation process. Whenever we look at an evaporite, we're looking at what is in effect a solar-powered mineral precipitate. So let's first of all define what is an evaporite. Well, it's a salt rock that precipitates at the Earth's surface in a hydrology that's driven by concentration due to solar evaporation. It can also form in the near surface as it does in a sabkha. But once again, this is the process of capillary evaporation driven by solar evaporation. These are solar-powered salts. In terms of the evaporite parent brine, there's no assumption as to its origins. It can be marine. These are sometimes called thalassic, non-marine or athalassic, or it could be a hybrid of a range of sources of brines flowing into a surface sump where that brine is then evaporated. There is a fundamental need for aridity, for the level of water loss to exceed the level of inflow of water. Accordingly, the deposition of evaporites is much more climate dependent than either carbonates or siliciclastic sediments. The other thing about evaporites is that they're highly reactive. The reaction rates are very much dependent on levels of solar energy input, and many of these reaction rates are reversible, especially if the chemistry of the brine in which they're sitting evolves. All of these reversible reaction rates are of an order of magnitude faster than anything we see happening in carbonate or siliciclastic. So let's focus in on the physics of an evaporating brine. Any body of brine at the Earth's surface or just below the surface where it's affected by capillary evaporation will, on concentration, accumulate a suite of salts. The mineralogy of the salts will depend on the ionic composition of the mother brine. But within that evaporating milieu of brine, there are a range of various physical controls on what's happening within that brine and between adjacent areas of the brine. So I want to consider a few of those. We'll look at density, and density increases as a brine concentrates. We'll look at temperature and how temperature can be homogeneous in a brine mass or be layered in a brine mass. We'll look at vapor pressure, one of the main controls on the rate of evaporation. And we'll also have a look at brine permanence and its back reactions. As a brine evolves, it can back react with earlier formed products. But before we do that, let's have a look at the fundamentals of what's happening in that evaporating brine. In that brine, we have solar heat being absorbed by the water molecules, and that's causing those molecules to vibrate, Brownian motion, and they will move with sufficient velocity that they can attain an escape velocity to break through the zone of surface tension. As those water molecules escape, the amount of non-water molecules, the cations and the anions left behind in that brine, will increase. What's actually happening in our brine is that we have solar heat absorption, increasing the molecular motion until a molecule can actually break out of that brine through the zone of surface tension. We have these water molecules agitating, taking up solar heat, solar absorption, and it reaches a point where they can actually break out into the overlying vapor phase above that brine body. When the molecules return, we call that process condensation. So at all times we have varying levels of evaporation and condensation taking place in a brine as we undergo that phase transition from a liquid in the brine to a gas in the air above the brine. If that air above the brine doesn't move, then that air interface above the brine will become increasingly saturated with water molecules. And it will reach a point where there's sufficient water molecules in that overlying zone to prevent further escape of water molecules from the brine itself. In other words, evaporation continues until we reach an equilibrium between the evaporation of the liquid, the escape of the water molecules, being equal to the level of return of those water molecules to the brine, the condensation. And it's that equilibrium situation which defines the vapor pressure of a brine. One of the factors that's also going to influence this is whether the air mass above that brine is static or whether there is wind blowing away that water mass above the brine, allowing more water molecules to escape from the brine pan. In 2021, Wood documents an interesting experiment that's been done in the Abu Dhabi sabkha. In that experiment, they laid out on the Sabka surface two evaporation pans, one containing brine, saline water, the other containing fresh water, and they monitored the weight of those pans over a diurnal cycle, over a bit over 24 hours, with weight loss indicating evaporation. But what's interesting is when we compare the relative humidity, which is the proportion of water in the overlying atmosphere to complete saturation, when we document that relative humidity, we can see that the evaporation pan, which was losing weight with evaporation, actually started to gain weight through condensation, water returning to the brine, once the overlying air mass had a relative humidity which exceeded 50%. Whereas if we look at the freshwater curve, that continues to lose weight throughout the experiment. And the difference is that in the saline pan, as water molecules are lost from that pan, we have an increasing intermolecular density. There's more cations and anions in there amongst the water molecules. And so it's much more difficult. Even though the molecules are still absorbing heat for at least a portion of that cycle, they can't attain escape velocity because they're colliding with the higher density of non-water molecules left in that residual brine. Whereas with the freshwater pan, it continues to evaporate. Throughout the diurnal cycle, the pan with the fresh water in it loses weight because there's nothing in that water other than water molecules. There's no cations and anions to interfere with the rate of evaporation. So there is what we call the evaporation factor associated with measured evaporation rates in saline pans. Now, many evaporation rates that you see documented use fresh water in the pan. So we have to apply a correction factor. This was known by Myers and Bonython as long ago as 1958, where they documented what they call the evaporation factor, which is the factor you multiply the freshwater pan measured evaporation rate to get a more realistic estimate of the evaporation in a brine. So the evaporation factor, as we can see here, is decreasing related to the increase in the salinity and the density of that brine. And also it's related to the level of moisture saturation in the air over the brine. In other words, as the relative humidity increases above that brine, we slow the evaporation rate. Moisture saturation in the air above a brine mass tends to increase over an increasingly saline water mass. And as we'll see in a minute, this is associated with the decreasing vapor pressure tied into more concentrated brines. But what this evaporation factor means is if we have a seawater-derived brine with a salinity around 200 parts per million, that's up in the gypsum precipitation rates, it has an evaporation rate that's only 85% of that freshwater pan. So this is the evaporation factor. It's always telling us that brine evaporation, it's lower because of that effect of increasing interference of the cations and the anions with the water molecules as the brine density increases. And here we can see it related to wind speed. This is for a seawater brine, looking at the relative evaporation rate, the evaporation factor if you like, versus the brine concentration. As the wind speed increases, so does the relative evaporation rate. It's because we are removing that saturated water above the evaporating water mass. So wind speed increases the evaporation rate over any water mass, be it fresh or saline. This change in evaporation rate that we see in the Abu Dhabi experiment is related to vapor pressure decreasing with brine density increasing. So we can see that with a greater concentration of ions and water molecules, we are going to decrease any individual molecule's kinetic velocity in that liquid mass as there are more collisions per volume of brine. And so vapor pressure, remember that vapor pressure is the equilibrium between evaporation and condensation. Vapor pressure is higher at higher temperatures as there's more energy absorption by the water molecules in that liquid at higher temperatures. As the density increases, as the salinity increases, the vapor pressure decreases, and that's true of both low temperatures and at higher temperatures. Obviously, the rate of decrease is much greater at higher temperatures than lower temperatures as the density increases. And that in turn is related to surface tension changes. Surface tension is what occurs in a water mass at a liquid-air interface. And it's the result of the greater attraction of the water molecules through hydrogen-hydrogen bonds, this gives it cohesion, Then we have when water is in the air mass above that water mass, where we have the effects of adhesion, not cohesion. Within the water mass, the net effect of those intermolecular forces is an inward force that is cohesively pulling together the water molecules. You can think of it as a stretched elastic membrane pulling everything together. It's why we see water droplets in a gas, and it's also why we see different contact angles, as we discussed in the petroleum course, with different levels of surfactants on the surface of pores. Because of this internal cohesion, this hydrogen-hydrogen effect, we see surface tension will increase with brine concentration and decrease with brine temperature. So fresh water has a surface tension of around 72 dynes per centimetre. For contrast, the only thing that's a liquid that has a greater surface tension than water is liquid mercury, which has a surface tension of around 700 dynes per centimetre. But that's because liquid mercury, we're looking at metallic bonds, covalent bonds, holding the molecules together, so it has a much greater internal cohesive strength, versus water, where it's the polar hydrogen-hydrogen bonds holding that water together. But you can quite clearly see here that surface tension is increasing with the brine concentration as we go from left to right, and the density is increasing. And also, surface tension is decreasing with temperature as we up the rate of vibration, the level of energy absorption with higher temperatures. We lower the surface tension in our brine. This is all these plots I'm showing you are for seawater. Likewise, if we consider brine viscosity, remember that viscosity is a measure of a fluid's resistance to flow, so it's a number that's capturing the level of internal friction in any moving or flowing fluid. And so viscosity, as you'd expect, tends to increase with increasing levels of intermolecular friction as the level of cations and anions increases as water molecules leave, as the salinity increases and the density increases. So viscosity will decrease with increasing temperature. Once again, higher levels of absorption, easier to escape the zone of surface tension, and it also decreases with decreasing density. So less saline fluids are less viscous. To put it into some sort of context, pure water, by definition, has a viscosity of 1 centipoise. Mercury, 1.5, milk, 3, kerosene, 10. If we look at the Dead Sea crystallizer pans, the pink curve there, we can see as we're getting up into the bittern stages, up around 1.3, 1.35, where we start to see carnallite coming out of solution, we have a viscosity feel to that brine similar to kerosene. Perhaps the most important factor that we look at in a brine is the density of that brine. And as we concentrate any brine, its density increases. In other words, the water molecules are escaping, and so the relative volume of the non-water molecules, the cations and the anions left behind in that brine, are increasing, so the density is increasing as the degree of evaporation is increasing. So this plot is for seawater. Seawater is given a degree of evaporation of 1. As we concentrate seawater, we can see that gypsum drops out at around 4 to 5 times the original concentration of seawater. Seawater has an initial density of around 1.04. By the time we get to gypsum, we're looking at values around 1.08, 1.09. Then we move on to halite concentration, where we're now about 10 to 11 times the concentration of the original seawater, and we have a density of around 1.2. By the time we get to the bittern salts, the magnesium sulfate and the potassium chloride salts coming out of seawater, we have a degree of evaporation of around 70 to 80, and we have densities of in excess of 1.3. That, by the way, is the density of some of the mineral phases, or not much less than some of the mineral phases that are coming out of that solution. The rule is, as our salinity increases, the density is increasing in any brine, be it a marine water, as I've demonstrated here, or a non-marine water. That increased density can become sufficient that dense brine mass will sink down into the underlying sediments. It can displace the underlying pore waters. It can also stratify, and it can also drive back reactions. Well, let's look first of all at a very important process on a regional scale, at a carbonate platform-wide scale. This is the process of reflux dolomitization. If we have a body of brine which is concentrating in a lagoonal situation, that brine will reach a concentration where it has sufficient density that it can displace the underlying succession, and it will displace it with dense magnesium-rich fluids. And that can change the pore fluid chemistry in the underlying succession, and it can drive dolomitization. It can also drive secondary porosity creation, as well as a whole range of other diagenetic processes, which we looked at in detail in our Dolomites course, when we considered in a lot of detail the brine reflux model for dolomitization, as it's one of the major reservoir forming processes in many evaporite-associated carbonates. But it's not just dolomitization that reflux can drive. It can also drive cementation. It can form halite cements. And it can also drive dissolution or leaching tied to the descent of underlying density plumes. This requires a homogeneous brine body. But if we have a layered brine body where we have less dense waters floating atop more dense waters, we can also see some other interesting diagenetic and thermal associations. We've known for many years that in coastal cave systems, we set up a situation, if we have seawater and freshwater, where we set up a density interface. And here we can see divers moving. We've just moved through that density interface from the less dense to the more dense seawater, and we're now below that interface. And here we are coming back up through that interface between the less dense overlying water mass and the more dense underlying seawater water mass in these coastal cave systems. And it's quite stable. But this same density stratification with a more dense water mass below, a less dense water mass above, that density stratification, and as I'll show you in a moment, the associated thermal stratification, is quite stable in many modern day and ancient evaporite basin settings. And that density stratification is an important process that we'll look at a number of times as we go through a range of important syndepositional and diagenetic processes in our brines. The schematic is illustrating the same thing. In the upper, we have a homogeneous hypersaline water mass. It's non-stratified. This is sometimes called holomictic or holomixis, where, as you can see in the salinity profile, it's constant salinity, and in terms of its temperature profile, it's near constant temperature. So there's no long-term vertical gradient in those temperature and salinity profiles. Contrast that with the other end member, which is the stratified, or in lacustrine, it's known as the meromictic association, where we have a fresher, less saline water mass, the mixolimnion, floating atop the more dense underlying hypersaline water mass, the monolimnion. So we form a halocline separating that less dense and that more dense underlying water mass, and we saw those divers moving up and down through that halocline in that cavern system in coastal Mexico. Quite often there's a thermal effect, which I'll talk about in a minute, related to the differences in specific heat capacity, whereby we not only see a density stratification, we see a temperature stratification with cooler surface waters and warmer underlying, denser, more saline water masses. This stratification and the passage in the non-stratified to stratified is also an important one in terms of evaporite textures, and we'll spend a whole module looking at how evaporite textures relate to differences between holomictic and meromictic stratification, how in holomictic situations we tend to get brine reflux processes being active, and we tend to form bottom nucleated evaporites across the whole floor of the basin, whereas in stratified situation, we don't accumulate bottom nucleates, we don't see brine reflux because we've got no way of concentrating that lower brine mass, and we tend to see only pelagic cumulates, crystals and phases that are precipitated in that upper, less saline water mass, perhaps a gypsum saturation, sinking down through that denser, lower water mass. So why do we see this thermal stratification? Why do we see a thermocline corresponding to a halocline in many density stratified, solar heated water masses? Well, it's related to the specific heat capacity, where specific heat is the amount of heat required to raise 1 gram of any substance, in this case seawater, by 1 degree centigrade. The specific heat of an evaporating brine decreases as the salinity increases. What that means is, for a given amount of heat input, a unit volume hypersaline water will show a greater increase in temperature than a less saline water mass. If we layer up our brine, if we have a more saline brine below, a denser brine below, and a less saline, somewhat fresher brine or water above, we will see a contrast in temperature. For the same amount of solar heat input, we will heat that lower water mass with its lower specific heat much more than we will heat the upper water mass. So we set up this thermal stratification. This is sometimes known as heliothermy or heliothermically layered brine masses. And there are many examples of this around the world. There's a whole chapter devoted to this later in the course, but I'm just showing you the profiles here. Here we've got a profile from Romania where the dense water mass is coming off a dissolving shallow diapiric salt structure. In the middle, we've got Solar Lake in the Sinai, where we have a coastal seepage situation with a denser lower water mass and a less dense upper seawater mass. And we have an interface at around 2 meters water depth. And in the third lake, Hot Lake, we have in a glacial kettle a density contrast and a salinity contrast as documented back in 1958. We can also drive back reactions in evolving brine situations. Back reactions occur in dense brines because all our evaporite salts are labile. They are in equilibrium with the conditions in which they formed. And so if those conditions change as salinity increases or decreases, or we see a flushing by a more dense brine displacing a less dense brine, those salts are going to be subject to alteration. And so we see a range of syndepositional and later alteration processes where we can preserve a variety of textures and replacement textures. We know, for example, that we can form anhydrite by the dehydration of gypsum. We can form glauberite as a back reaction between a sodium sulfate brine with earlier formed gypsum or halite. We can form polyhalite as a back reaction as we evaporate a potassium magnesium sulfate brine, a seawater brine, back reacting with earlier formed gypsum or anhydrite or glauberite. We'll look at these processes in a lot of detail later in the course when we look at different types of marine and non-marine evaporite and their evolution. For now, I want to point out that with an evolving brine, with a dense brine displacing a less dense brine, drive a series of back reactions and alteration processes. And these processes don't just happen in the surface waters or the near surface waters, they can also happen in the subsurface waters. They can happen throughout the mesogenetic burial realm and the telogenetic, the uplift realm, as we'll see as we develop our ideas on evaporites and their evolution in the subsurface. The last thing I want to talk about is whether or not the brine contains minerals that are prograde or retrograde. A prograde salt means that if we cool the brine, we will precipitate that salt. It's reflective of the fact that in prograde salts, the average kinetic energy of the molecules in the brine increase with temperature, and that increase in kinetic energy allows the solvent molecules to more effectively break apart the solute molecules, and so the solubility of a prograde salt increases. Halite, sodium chloride, is a prograde salt, as is sylvite, potassium chloride. If we cool a halite-saturated brine, we will precipitate more salt. For example, if we have reflux taking place below a sodium chloride-saturated system, we can create halite cements in the underlying eogenetic flushed realm. Now that contrasts with retrograde salt. So retrograde salt has a solubility where it becomes less soluble with heating. The most obvious and the most prevalent evaporite salt that is a retrograde salt is anhydrite. Anhydrite has retrograde solubility. You can see from the curve that as the temperature increases, the solubility of the calcium sulfate, measured as calcium in solution, decreases. That has significant effects. It explains why we form nodular anhydrite in many coastal sabkas where we have resurging calcium sulfate saturated groundwaters rising and heating and hence precipitating anhydrite nodules. We can also see anhydrite as a very widespread hydrothermal mineral in a lot of deposits associated with black smokers on mid-oceanic ridges where we have hot hydrothermal waters driven by magmatic heating as we're forming new oceanic crust. As those hot hydrothermal brines come into contact with seawater, it heats the seawater and it precipitates calcium sulfate. And calcium sulfate, during the formative stages of the smoker deposits, is a dominant phase. Most black smokers contain significant levels of anhydrite, and all the white smokers that we see from the cooler brine systems are dominated by anhydrite because of its retrograde solubility. They're not evaporites. They're forming because of the heating of the brine by escaping magmatic or hydrothermal waters. But they have the same mineralogy as anhydrite forming in a sabka. And we'll look at how to differentiate those deposits a little later in the course. But it's a very important distinction to make between prograde and retrograde solubility in evaporite minerals, and it has some fundamental implications. In summary, what is the process of evaporation? Well, solar concentration of brines makes them denser and more viscous. If we have a layered brine mass, the bottom brine mass, because of the difference in specific heat capacity, will be hotter in that more dense, lower brine. Brine evolution, especially where we have dense bottom brines displacing less dense brines or a mixing between two brines, or the evolution of a single brine body as its salinity and chemistry changes with ongoing concentration, we can drive back reactions as well as reflux alteration of underlying and adjacent sediments. The evaporation process, by definition, puts water molecules into the air above that evaporating brine mass. Whether or not that air above remains saturated with water, the humidity of that air mass controls the rate of evaporation. And so if we don't remove that overlying humid air by some sort of wind action, we'll actually slow the evaporation process down. That can control the rates at which various evaporite minerals can form. So the evaporation process isn't just simple drying up of a water body. There are a whole range of physical processes that interact and change the chemical and the physical evolution and the hydrology in our evaporite depositional system, and subsequent to that in the subsurface as our evaporite brines continue to evolve.